Пишу, чтобы не забыть.
Okay. Few very quick organizational announcements. First one is we put closing remarks on the schedule, and I suspect that probably not very many people will show up for closing remarks. So we will stay for maybe 2 extra minutes after Nikita's lecture to officially say thank you, and the closing remarks after lunch or after whenever after exercises, we'll just extend the exercises, problem solving, and informal discussions part. Okay, and we have the last lecture of the workshop and the last lecture of Nikita's course.
So our goal in this lecture course is to connect the two stories, the story of enumeration of instantons or integration of modular spaces of sheaves, and the story of integrable systems, quantum integrable systems, classical integrable systems. And it's a big, both stories are very rich and vast, so I only touched on maybe some aspects of those. But I want to connect them today, and my goal would be to arrive at this blackboard with at least with understanding of the origin of Lax operators of integral systems from the geometry of modular spaces of instantons and their generalizations. Before we do that, I want to comment and maybe explain why these observables, which we introduced yesterday, or the day before yesterday, why they were called Hugo characters, and so why they're characters. And that will, so one way to illustrate it is to generalize the problem and these observables, and that in such a way that the classical Lie algebras and the root systems associated with simple Lie algebras will appear, and then these observables will be indeed related to the characters of the mental representations of the Lie algebras. In particular, Coley asked me at some point how does it work for other root systems. So I just want to sketch the construction, and it will be useful also in understanding some aspects of this relation. So, okay. So what were we doing yesterday? So yesterday we said that we were studying some kind of enumerative problem, which by localization became a statistical mechanical problem for, and the problem originally was computing some integrals over the modular space of sheaves, and the sheaves were living on a two-dimensional, complex two-dimensional plane, which I called C212. And I mentioned several times, and in Andrei's lecture, you heard today that it is actually, we should think of this C2 is sitting inside a four-dimensional complex manifold, in fact, Calabi-Yau fourfold, which is locally a four-plane with coordinates 1, 2, 3, 4. And so there is a transverse, there's some transverse space which intersects with our plane only at one point. And so that plane was C234. So then yesterday we started playing with this problem and introduced the defect, which was, so the defect was obtained by performing an orbifold, which was acting inside a two-dimensional plane, which was and so we had an orbifold in this space, so that when you observe it from the blue point of view, you only see that something is happening along a line, along a complex curve. or along a two real dimensional surface, and so that looks like a surface defect to the observer who is attached to that plane. So he sees just a surface defect. But of course, to the observer who looks at it from from beyond, right? The sees it as a two complex dimensional object. I want to be gender neutral. So, but now when you look at it, you can ask, but why did we do this? Why only C2-4 plane? Why couldn't we do some kind of orbifold in, let's say, 3-4 plane? And what will the again the Earth observer living on this plane of reality will see? And so let's do that. So let's. So let me redraw that picture. Again, this is C2, 1, 2. And so we have some rank n sheaves, or for physicists, UN instantons. And now I have the transverse complex two-dimensional plane. And I want to modify this geometry in such a way that the observer who lives here doesn't see anything at all. So for this observer, the world is flat and carried on three turtles, and so everything is nice and quiet. But the transverse space is modified, and so let me modify it by introducing some group gamma, which will act here and introduce some kind of orbifold structure. And so what are the natural groups? Well, because of various considerations of supersymmetry or maybe symplectic structure for algebraic geometry, it is natural to take the group gamma to be a subgroup of SU2, or SO2 for algebraists. And there is an ADE choice of these subgroups, but let me not kill you with the. No, there is no. So I see. So this guy sees world is flat, no defects. No, here the world was not flat because it was a surface defect. So something was going on along the two-dimensional surface. There was some, there is some bump on the road. But here nothing is happening. It's No, you do. No, of course not. This, you look at all rank n torsion-free sheaves. It's just localization. Because you have the framing at infinity and you localize with respect to the maximal torus of the framing. It's a, so it's a product of, so your sheaf will split as a direct sum. of rank 1 torsion-free shifts. Yes. No, you integrate over all, but the fixed points of the framing group action would be the split shifts. I mean, it's just all right. So this is what we want to do, and in fact, there is not much you need. Okay, let me take as an example. So this example, and this is a special example, but it's connected more directly to what we are doing here. So let me take the group to be ZR plus 2. Apologize for strange notation. So it acts by Z3, Z4 going to omega is the primitive root of unity. And now we just, okay, so now I also need to explain, so my framing space. So what you probably have also inferred from Andrei's talk was that this n rank n shifts, they sort of correspond to doing something on the kind of flattening of this plane, and this flattening is of kind of length n. So if you try to think geometrically about what this rank n shift describes, they describe kind of surfaces with multiplicity, and this multiplicity is sort of spread out in this transverse direction. So these n guys, guys, they actually look like so what I'm trying to say is that you should think of this rank n as sort of corresponding to n points, kind of n points dancing on this transverse plane. Okay. And now that I have the group action, and the group acts on this plane, well, it might act on those points somehow. And so we want to, so there are different ways of different group actions depending on how this group acts on the collection of those points. And so one kind of, again, the simplest way to let the group act is to say that these points actually form orbits of this group. And so in the sense that you say that this is the space of kind of functions on n. So this is boldface n. This is the number n on n copies of gamma orbits. In other words, I'm trying to represent something which on the quotient space, and the quotient is actually, well, it's a singular space. So this is the C2, 3, 4 divided by gamma. We discussed those quotients for r equals to 0 at one of the previous lectures. But so again, we can. So if you introduce the invariance, I'll change notations. That as an algebraic manifold, this is just a surface described by the equations AB equals C to the power R plus 2. Wait. So I just want to say that on this quotient space, I have n points. Okay. So n points here. And each point on the quotient space, unless it sits at the singularity itself, will lead to to an orbit. So this is one orbit, this is another orbit, and so on. So on the covering space, it means that I have n times r plus 2 rank n times r plus 2 sheaf with gamma action. Yes, what's the question? So you see, okay, these are sheaves on C2. But what I'm trying to describe a kind of a fiber. The fiber of the sheaf should be viewed as a space of complex functions on a zero-dimensional scheme on the transfer space. Yes. Right. So somewhere in the sky there is the rank 1 sheaf, and we push it forward down. Well, yeah. So because of n copies, but
Can I understand? So if you have Rankian sheaf on the surface, are you saying that this is a torsion sheaf on factoring of the surface?
yes.
But this torsion sheaf is only
It's a torsion-free. It's a torsion sheaf on this four-dimensional space.
Which is still set theoretically supported on that basis.
Yes.
But okay, but then that's not exactly supported everywhere on that file, right? It's just set theoretically is still supported on C. Can't go so far in the file.
No. Of course, this is all infinitesimal picture, so to speak. I'm just trying. Yeah. We have. I mean, this is getting inside the meat of the problem. Of course, there are. I mean, we're not just counting sheaves. We have sheaves, and we have sections of adjoint bundle twisted by this normal bundle. So in principle, there is room for actually going, finite distance in this space. That's just a question whether you have solutions where the Higgs field has non-trivial values. Just since we work equivalently with respect to many symmetries, including the torus which acts on that space, we actually cannot move anywhere outside this point because of the torus symmetry. But if you remove this symmetry, then you can go all the way. Okay, so all this is to say that the space N and its character will now split as a sum over both the colors which we had before and the new object which is the representation which is the reducible representation of the group gamma. So the group gamma, being cyclic group, has a ring of representations which is generated by one-dimensional reducible representations. So let me just call it like that. So R0, R plus 1. So these are irreps where the generator of the cyclic group acts by its S power. So S goes from 0 to R plus 1. And so I just, for each representation, for each reducible representation, I have an n-dimensional sheaf. So I have an n-dimensional vector space, which will be the fiber of the trivialization of my sheaf at infinity in that space. And these are now equivalent parameters for the framing group acting there. So the framing group is now GLN to the power R plus 2. So for each irreducible representation of my group gamma, I have its own framing. And so if you formulated the problem of doing instanton counting as an integral of, is it Reith product? Maybe it is a Reith product, yes. These are actually invariants. So for me this is the so this is the subgroup of the huge framing group, which commutes with the group Z. It's not a Reith product. Okay, so the modular space of now let's call them quiver instantons. It's just it's the ZR plus 2 invariant locus in the derived modular space of framed rank NR plus 2 sheaves on P2 with trivialization over P1 at infinity. And now this trivialization involves, so the trivialization is now includes the group, the decomposition of the fiber at infinity as a representation in irreducible representations of the group gamma. And my requirement here is that the ranks of the isotypical components are all equal to m. So that's this is what it means to be a regular sheaf. Now the new phenomenon is that well, basically it means that it's just a collection of torsion-free sheaves. So EI is torsion-free on P2. It is trivialized, sorry, ES. It is trivialized over P1 at infinity. And what else? So they all have ranks equal to n, and they have, but they can have different Chern classes. And so this space is the disjoint union over now the vectors of instanton charges. And so in doing the counting, we will be summing over these charges with new parameters. And that's the proliferation of the coupling constants, which we also saw in this example. So it means that what used to be the single Q will now become a collection of Q0, QR plus 1. And so we'll have the Z function and other functions which are now collections of, so the arguments are now all of these covariant parameters, the vector of Q couplings, but we still have the three parameters epsilon 1, epsilon 2, epsilon 3, because the symmetry, we still have the symmetry of rotations of this plane, and we also have a symmetry of rotation of that plane. What's so special about the cyclic group is that well, it commutes with the torus section, so we don't lose any parameters. If you take the dihedral or icosahedral or I forgot what they called. So the groups which are the Kleinian groups which correspond to the exceptional series, then they actually they will rotate Z3 and into Z4, and so we will not have the independent symmetry of with the epsilon 3 and epsilon 4 parameters. So it will we will have to impose an additional relation on epsilon 1 and epsilon 2. So that theory is slightly more complicated because of that, because they have fewer parameters to play with. But for now, let's stay within A series, and so okay, instant on here. And then we have this huge product over. Oh, sorry. Of course, we'll have that now the sum over the collections of partitions, which now will be labeled by two integers, alpha and s, because for each sheaf, it will split into sum of Rankine sheaves, and they all are monomial ideal sheaves, so they're labeled by their own partitions. So these are. So it's now n times r plus 2 tuple of Young diagrams. And so the number ks is just the sum over alpha from 1 to n of the size of diagram under S. But then the measure which you put here is can be obtained, simply from the formulas which we had already by the simple rule. So you write the formula for the theory with the gauge group of that rank, and then you just keep terms of zr plus 2 charge equal to 0. So what is the charge? The charge. So again, we'll assign the charges to this parameter. So this guy will have charge s. Just read it off the index. Epsilon 1 and epsilon 2 have charge 0. Epsilon 3 has charge 1, and epsilon 4 has charge minus 1. So you take the expression from Wednesday. So these expressions were some linear functions of A, epsilon, and epsilons. And then you just compute the charge of the linear combination of this expression to be simply the sum in alpha s times s plus m3 minus m4 modular r plus 2. So if this is 0, then you keep this factor, and if it's not, you just throw it away. So the big gauge. So that's this is the thing which is hard to understand in quantum field theory, but this is what you learn in string theory course. So this is the big gauge group doesn't exist actually. It was. Yes, yes. I mean, maybe it exists in some, in this, if you add back all string excitations. So this becomes D-branes. We're doing some kind of open strings, and but this orbifold projection is a projection. No, it does not exist. So the gauge group is what survives the projection. Yes.
One question is, if I start from this portion G,
Maybe sorry, Ardan. No, of course, I'm speaking from the perspective of quantum field theory, but these days one should speak from the perspective of condensed matter theory. And in condensed matter, gauge symmetries and all kinds of projections, they are all effective things. These are things which exist at low energy. So, for example, there is famous Kitaev toric code, which is a kind of a gauge theory. In his approach, all gauge constraints are just low energy approximations. So maybe there is some bigger theory in which right. No, these are so the instantons will be with this gauge group. So these are the instantons which I'm counting. Right. Of course. Yes, yes. So it's a collection of R+2 UN instantons, but the whole story is that these are now instantons with matter. So this word derived means that from the conventional physics point of view, it's a theory with bifundamental hypermultiplets. So they talk to each other. No. So they solve different equations. They solve this non-abelian Zabik-Witten equations with matter fields. Well, on the localization locus, they are actually instantons. The matter fields vanish on the solutions of the equations, but the fluctuations contribute to the integral, and that's what we are discussing. Yes, that's what I'm doing. I'm just explaining quiver gauge theory in this geometric way. Yes.
in that partition function, if you start from G, rank n over its own support, push it forward onto the support, kind of roughly what you're doing when you look at the first case locus. Then on the base C2, the rank is the same, but then you have many ways of decomposing this rank. Perhaps 1, 1, 1, 1.
So when you do it carefully, and let me draw the picture which Andre alluded to. So let me just draw the picture. Maybe it will answer 1,000 questions. So the picture is the following. So we organize the representations of the group ZR+2 into Mackay graph. So what is this graph? So the vertices are representations, R0, R1, and so on. And this is R+1. And the edges are decompositions of the tensor product of each representation with a two-dimensional representation which I have defined for you. But this is my two-dimensional representation. So it decomposes with some multiplicities. And so these multiplicities are encoded in this graph. So of course, it's a two-dimensional representation, which is actually a sum of two one-dimensional representations. And so if you multiply this guy, you'll get the sum of these two. If you multiply this guy, you will get the sum of these two, and so on. And now, in doing what I did, you promote these vertices into vector spaces. And in fact, you promote them into sheaves. So they become sheaves of rank n. And so we study the modular spaces of those sheaves, but on top of those sheaves, we should think of these modular spaces of abstracted space with abstractions coming from derived homes between sheaves connected by the edges. And so that's what we're doing. So we integrate over the product of the usual modular spaces of frame sheaves. So the equivariant, I mean, again, well, some kind of elliptic class of those things. So some, and then epsilon 3 is the argument of this elliptic class. Yes, so this is called A R plus 1 hat theory. R equals minus 1 is the minimal one. It's when I do nothing. And so that's a 0 hat which we started with. So. Okay, so it looks like I'm complicating things, but I actually want to simplify things. And all this is done for the sake of illustration. And so to arrive there, let me now take the limit. So the example continued. So now I set Q0 and QR plus 1 to 0. So what it means that of this chain of sheaves, these guys are now just fixed vector spaces. So just trivial sheaves, just vector spaces. No. So okay, for the experts, for the experts, the mass of the bifundamental which connects the nodes S and S plus 1, the fundamental field, is computed as follows. It is epsilon 3 over R plus 2 plus the difference of the U1 parts of the Coulomb parameters. So it's the sum over alpha from 1 to n, alpha S plus 1 minus A alpha S. All right. Okay, let's spend more time. So why is this a simplification? Well, because then actually things start looking much simpler than they looked before. And in particular, if let's say R is equal to, so this gives me a R type theory. So as you can see, this is now, this part is a Dinkin diagram of a R type. And these are just some decorations. So in particular for the A1, let me just tell you what is the measure which we will get for A1 theory. So now A1 means that so I only have, so now S goes from 1 to R. This is why it was some strange choice of the group ZR plus 1. So now we have only R times N partitions to sum over, and for A1 we'll have our good old set of n partitions, and this measure will be now the product of alpha prime, and we'll have the denominator, which are the products of the partitions as before, with legs and arms. But the numerator will be now a different type of object built out of Young diagram, which follows by this projection. So this is an interesting fact about the. Okay, so what it will be? It will be A alpha minus M. So now I will introduce notation. So A0 S, which we still have, I will call M minus S, and AR plus here. So notation. A0S will be called M minus S, and R plus 1S plus epsilon 1 plus epsilon 2 will be called M plus S. So yeah, so you have bifundamentals for the middle nodes and fundamentals for the two. And for A1, there will be only two fundamentals. Yeah, but this is general. Right, this is general. Right. So, okay, yes, and that's what I want to say. So I'll get. So this will be the content polynomial. Times, and then the product over S from 1 to n. So these are contents of boxes. So in denominator you have arms and legs, and numerator you have contents. And so that's and you got it just by doing this general procedure. But it's much simpler. It's much simpler theory to analyze. And now to this whole picture of this beautiful world, we'll now add the Q character, QQ character. So now I will add one-dimensional object, so the rank 1 sheaf extending in that direction. So this guy is no longer happy. What? So something happens at one point, and well, for the general theory, we'll have to take the formula which I wrote, which was the sum over one partition, and project and do the orbifold projection. But now, in this simplified case, the QQ character. So first of all, sorry, I should explain one thing. So, when I say rank 1 sheaf, now because of the orbifold structure, because of the orbifold group acting on this space, I need to specify also how does it transform under the group action. And so we have, even for rank 1, we now have R plus 2 choices, because the fiber at infinity can transform in one of these irreducible representations of the group. And so we have, that's why we'll have not character but characters. So they will be labeled by so fundamental QQ characters. They will be labeled by the letter S. It will be the functions of x. And Oh my God, I need to start with the definition of the y observable. So the y observables also get the orbifold dress. So that's, but that's kind of easy, and that's almost. So now we'll just have. Yes. You see, I have Laxaprint. No, I said that we'll go back to the complicated case of A0 hat, but we need to first grow some muscles. And so we'll deal with simpler linear quiver type theories first, and then we'll go back to this. Yeah, of course, these theories also correspond to quantum integral systems. They're just not Calogero. They're Calogero with spin degrees of freedom. Okay, so first, so if I have a, so the y observable, which was, remember, it was a sheaf, which was essentially a fiber of the tautological sheaf at this point. So now this tautological sheaf has, well, this point has an orbifold action, and so I need to specify which representation I'm taking. So let me just write the formula for you. It's the same formula we had before, but now it's I'm just a little bit refined because it has now this additional index. It is the same formula. I'm just using. So just put the index S at appropriate places. It is a little bit misleading that it is so simple. Maybe in the exercise session, we'll compute the y observables for the in the presence of the surface defect, which is a different orbifold. There you will see that it is a little bit different. It is less simple, but still straightforward. So basically, I'm just introducing the y observables for each of these gauge groups. Very, very natural thing. So this should go like. So you could repeat the same story. We start with this observable. Its expectation values will have poles. We'll try to cancel them. Now the cancellations will depend on which instanton, so in which gauge group the instantons are sitting. And something interesting will start happening. Because now the nodes of the quiver will start talking to each other. So you see, I canceled the poles in the summation of a Young diagram corresponding to the node ES, but then I introduced the poles from S minus 1 and S plus 1, and so we'll need to close it up. Yes, right. So all this, this formula is just it's the same summation over the single Young diagram we had before, but now this Young diagram is colored, and now it is colored according to the ZR plus 2 action. So now if I draw it carefully, or try to draw it carefully, if this is Z3 and this is Z4 direction, so now the colors are according to the distance to the diagonal. So these guys, so my diagram, so the rule is the following, that you give this box color S. So this is ZR plus 2 charge S. And so all these boxes have charge S. And now in this direction, Z3 grows, so this box will have charge S plus 1. So the color is blue. And these blocks will have charge s plus 2. And so the weight of the diagram, so the weight of that diagram will be qs to the power 3, and then qs plus 1 to the power 2, and then qs plus 2 to the power 2. But in fact, okay, so now, because of the periodicity, if the diagram grows sufficiently far away, you may get additional contributions. But now, if I'm in the AR situation, where Q0 is equal to 0 and QR plus 1 is equal to 0, if my diagram grows too far to the right or too far to the left, its weight will be killed. Its weight will be 0. So only lambdas for which every box, so every box lambda has ZR plus 2 parity charge equals to S plus I minus J, they should be strictly above 0 and strictly less than R plus 1. So once again, the weight of the diagram is the product over all boxes in the diagram, Q with the index S plus I minus J. So this is what replaces what we had previously as Q to the size lambda. So this is the weight. And now, so I don't want Q0 or QR plus 1 appearing in this product, because that would kill the contribution. So that restricts my choice of lambdas. And so there is only a finite number of lambdas. And in fact, this finite number is equal to R plus 1 choose S. And in fact, these are fixed points in the Grassmannian, Schubert cells, or vectors in S fundamental representation. Say it again. Say. Yes. So I'm. No. So those homes, they were in the measure which I erased. So this is now something new. So this is counting in your language. So this is counting homes between this rank 1 sheaf and that and those. Yes. So these are these things. Right. Okay. So so the QQ character in this case ends up being a rather simple thing. So let me write the formula for you. So okay, remember, so by this rule, y naught of x is just a polynomial, just a product of I should have, sorry, this is wrong notation. This is 0. This is alpha, so alpha. I apologize. And similarly, yr plus 1 of x plus epsilon 1 minus epsilon 1 minus epsilon 2 is product simply because for the nodes 0 and r plus 1, the partitions are empty. So the boundary consists of just single box with the trivial content. And so this is what it is. So now I can write the formula. Let me introduce a shorthand notation. Epsilon without index is just epsilon 1 plus epsilon 2. And then it's a sum over all L element subsets of the set containing 0 to nr plus 1. And this is the product from B from 1 to L, Z, I, let me write like that, lambda I, B, B. Okay. Where I introduced, again, so I apologize, I have to introduce a little bit of notation. So lambda I of x is zi times yi plus 1 over yi. I from 0 to r plus 1. And zi is z0 times q1 qi. So this is some excessive notation, but it is convenient for calculations. So if you ever looked at Frenkel-Reshetykhin paper on Q characters, you would start recognizing something. Okay, so lambdas are kind of quantum eigenvalues of something. And where are my notes? My notes. Okay, made a mistake. Minus L. So it looks like it looks like you're doing some kind of symmetric functions of these eigenvalues, but the arguments are shifted from time to time. So this is a little bit of non-commutativity going on here. So now let me do a very, very fast forward. How much time do I have? Okay, super fast forward. Say some keywords. Let's take epsilon 1, epsilon 2 going to 0 limit. So then it turns out that in this limit, the expectation values which we were computing, which we were discussing, and so on, they factorize. So I'm talking about properly normalized expectation values. So this is 1 over in this limit. This is in this limit. So this is called the limit shape phenomenon. And so it goes back to Vershak and Kerov, Logan and Shep from the 70s. And the main importance of this limit for us is that, on the one hand, I told you that the expectation values of the QQ characters before taking limit, they were analytic functions of x, have no poles in x. Yet, by inspection of this expression, you can see that, let's say, in cohomological theory, well, in any theory, actually, so it has no poles, so it's a holomorphic section of some line bundle, and these expressions, they are sums of terms which are all sections of line bundles of the same degree. And so this whole thing is a holomorphic section of some line bundle, which is good. On the other hand, we can now, in this limit, we can relate this expectation value Okay, let me call it Ts of x. So some of degree n line bundle over elliptic curve. This is the elliptic curve of elliptic homology theory. On the other hand, by this factorization property, this is equal to the expectation value of the product of expectation values. And so we can sums and products of expectation values. So this was before taking the limit. And now we have that Ts of x is just the sum. So it's y0 of x times the elementary symmetric, so divide by the product z0, zs minus 1, times the s elementary symmetric function of this quantities lambda. So lambda 0, lambda r plus 1. So where now lambda, these are actually expectation values of so the zi. So now lambda I is the expectation value in the limit. Okay, so we now have a system of algebraic equations. So you need to start by if you fix some polynomials or polynomials or some theta functions of degree n, and you want to recover lambdas by inverting this relation. So how to do that? Well, the simple way to do this is to compute the introduce a generating function. So let's multiply it by this product, multiply by Ts of x, and multiply by variable z inverse to the power s, and let's take the sum from 0 to r plus 1. So then this is going to be just the product y0 of x from 0 to r plus 1, 1 minus z inverse zi yi plus 1 divided by yi. So the left-hand side, let me denote it as rxz. So it's a holomorphic section of line bundle of degree n with respect to x, and it's a polynomial of degree r plus 1 with respect to z inverse. So there's some finite dimensional set of parameters which control this thing. So this is kind of algebraic object. And the set of zeros, so if I set this to 0, I'll get an algebraic curve in elliptic curve cross P1. So the elliptic curve is where x lives, and P1 is where z lives. And what does this curve describe? It describes the sheets of this function. So zi. That's very wise observation. So zi's are fixed parameters. They were my coupling constants. Notice just one equation. It just has this equation has many branches. So these are branches. So I'll start using this breadboard because we are getting to closer and closer to where we want to get. And this is what we were working on with Igor Krichever. I mean, the last months when he was with us. So this is really very much in the spirit of his view of many things. So if I draw this in this way, so this is x. Very good, very good. No. Z naught and etc. are fixed variables. Wait. Let me draw this. Okay, so I'm drawing this now for the. Let me go to the rational limit so that I can draw things. Well, there are no good formulas in any case. Okay, let's not slow me down for the moment. Let me say something and then we can discuss. So over this point, my curve. So this is x plane. So this is infinity on the x line, and then these guys will be the points which Vanya is talking about: z0, z1, zr plus 1. And now the curve is it's a set of zeros of this equation. So then it will do something. And over. Okay, maybe I should have written it another direction. Okay, what did you want to ask? There are no good formulas for y's in any case. So the formulas for y's are the solutions of an algebraic equation. Go to Galois, for good formulas for y's. Yeah, but it's as good as it gets. No, it's as good as it gets. But the point is, so which I should have said, was that nevertheless the original parameters, the original variables a, which we had to fix, so they will be related to the periods. Yes. So the genus is what you want. So the genus, this curve, is the product of R times n. Well, it's a curve of so just by counting degree and using a junction formula. Okay, so you get the curve. So this is the curve. So this is the curve, and we want to say that this is a spectral curve. But it's a spectral curve of what? So we need to produce an operator for which. So my claim is that there is an operator also, such that the determinant of that operator, which depends on two variables x and z, is equal to this object here. So let's build that, and then we'll discuss the details. So to get the operator, we need to now do both things. So we combine this orbifolding which we had before, and we introduce the orbifold in the 2-4 plane. So now add surface defect. And so we add surface defect by introducing also the n orbifold. And so in a sense, we are dealing with a orbifold structure with respect to a bigger group. And so the representations of this bigger group are labeled now by two integers. So this circular or linear quiver structure will get an extra dimension. So now each thing will become. So this is now Zn cyclic structure. And so on. And so that starts approaching, so that becomes, so the whole thing starts looking like a lattice model on the two-dimensional torus. But very concretely, what will happen will be that now each y observable s ys will become now a bunch of y observables. So now omega, so S labels representations of the R group, and omega labels representations of the N group. And so this guy is now, so I'm writing this, okay, so this is, and then, so this is going to be the product over all partitions of a given type, S, and here, so here the condition so this is if beta plus j minus 1 is equal to S modulo n. So this is an example of the projection. Okay, so this is delta beta plus. It means what? Means what? So who is not zeros? Oh yeah. So back to the general case. Yeah, back to general case. So I'm writing the formula for. I'm writing a microscopic formula first, and then we'll go to limit epsilon. There will be what? Well, wait a second. Okay. So now basically I can organize this rectangular collection of observables into a collection of diagonal matrices. So I will. It turns out that it is you can package everything into matrices. So I keep the index S, which is the quiver index. And organize, okay, n minus 1. So it's a diagonal n by n matrix. Why is it a matrix? Well, because of this shift. So if you have good eyes, you will see that I have one condition in one factor and another condition which has a shift by 1 in another factor. So it turns out that the way to organize these quantities into fractional QQ character, which is now, which is what will encode the limit shape of the system, you write the product of matrices. And the matrices will have the form C hat, Z hat, y0 of x. So this is in the limit epsilon 1, epsilon 2 to 0. But the thing is that this is the similar sum. So it's a sum of the matrix product now, Z0, Z hat, S minus 1. And then it's a matrix of the QQ characters, X, And then there is, okay, make it product. Let's see. Z. So where C, so heads stand for matrices. Heads means not everything is diagonal. So that's so far Y's are diagonal, but there is one non-diagonal matrix in this business, and it generates the rest. So, there is this matrix C, which is a cyclic shift with the multiplication by Z inverse at the end. So it's a matrix nth root of Z inverse. And so this little shift which you had in these formulas can be packaged in the following statement that this matrix product, so it's a product which is ordered in some way, I think it's in that way, in that direction. So it has R plus 1 factors. The claim is that if you open brackets and decompose and reorder things, so you have so here you have this shift matrix raised to the power S. The coefficient of this object will be the collection of the QQ characters, so fractional QQ characters. So this is again a diagonal matrix whose entries are now the fractional QQ characters. And the main theorem about fractional QQ characters is that the expectation values are also regular. So Z matrix, it's a diagonal matrix again, so its entries are Zi omega, and so Zi omega plus 1 over Zi omega is Qi omega. So now that we have both quiver and the surface defect, we have these fractional couplings in abundance. So we parameterize them in this way. So this is regular, and so it's a holomorphic section of degree 1 bundle. And so that's the whole excitement, that it's just degree 1. So it has only one. It's degree 1 because of that. You see, by doing this Z-on orbifold, I've managed to factorize my Y observable into products of something of rank 1. So more geometrically, so the Y observable without surface defect was it was a kind of fiber of the rank n sheaf, and now with the surface defect, I'm splitting into one-dimensional components. Just splitting it with the surface defect. And so this is holomorphic section of degree 1 bundle. And now I'm organizing them in this diagonal matrix. And so now this is an operator. So let me call it d hat of x and z. And as a function of x, now we take a limit and do everything on the expectation value. So this is now expectation values. And look at what have we achieved. This is an operator valued function of x and z. As a function of x, it's a linear function. It's a section of degree 1 line bundle. As a function of z, well, it's still a polynomial of some degree, but it's built out of very simple things. So if I want to reconstruct these entries, I need to learn how to factorize a matrix into the product of matrices of the form 1 minus a shift operator. And Anton Jamai here is one of the experts on that in this business. But if you're a very simple-minded person, we just look at the solutions of the equation, this is equal to 0. Sorry. So if you solve this equation, well, it's a matrix product, so one of the factors will have to annihilate this guy, and so you can actually recover the entries from the eigenfunction. So if you know the if you know the kernel of this operator, you will recover eventually these guys. There's a bit of course of a story of how to deal with the multivariateness and so on, and I will not get into that. So what's the relation of that? So just I'm almost finished with this part of the story. What's the relation of this matrix equation with this equation? That's the relation. Okay, let's get no. We get Lux operator without. This is the relation. So the relation is this one. This is the relation. If you take the determinant of this operator, the right-hand side or left-hand side, the left-hand side will be the product of determinants. And then simple fact about the products of shift matrix and diagonal matrix. If A is a diagonal matrix, then the determinant of this guy is simply 1 minus the inverse determinant of A. We can do it in exercises. So the determinant will factorize, and long and behold, these y's without hat are just the products of the fractional y's. So these are just determinants of the y's with hats. And also zi's are determinants of capital Zi hats and so on and so forth. So if my determinant vanishes, which is where my spherical curve sits, then this operator has a kernel, and so then I can play this game of solving for these y's. Now, where is the Lux operator? This is not yet the Lux operator of the form we understand. Let me do it in a rational case, and I'll leave it to you as an exercise to do it in the elliptic case. It's not, it should not be that difficult. In the rational case, because D is a degree 1 polynomial in X, there is a general formula for degree 1 polynomials, right? So this is X times D0 of Z plus D1 of Z. Now, D0 of Z is actually a very simple thing. In order to extract D0, we just need to take a limit when X goes to infinity. And the only way we can get something linear in X is that we extract X from here, and here we just replace them by unity. So D0 is simply the product of 1 minus C hat Zi hat. So we can write this as D0 of Z times X minus L hat of Z, where L hat of Z will be now the Lux operator, which is D0 Z inverse D1 of Z. So now this object has singularities in the Z variable, because by this formula, the determinant of D0 of Z is simply 1 minus Z inverse Zi. So singularities, so the poles, so poles of L of Z R at Z equals Z0, Z1, ZR plus 1. And therefore, so we can rewrite it as a sum with some residues. And because of the nature of this operator, the residues will be rank 1 matrices. Simply, why they are rank 1? That's simply because, well, when you invert an operator, which is a polynomial in Z, the residues, so the poles are at the zeros of the determinant, and the residues are essentially the projections on the kernel and of the kernel of a dual operator. Li hat depend on everything. The L hat depend on Z hat, and if you like, yeah, maybe you can organize them into A's. Yeah. So they contain information both about the theory without surface defect, which from the point of view of integrable system are integrals of motion, and but they have twice as much information in there because the surface defect brings the data of these ZIs, which are not visible in the bulk theory. And so these are actually degrees of freedom which actually change in the Lux flow. No. ZIs are the parameters of the surface defect. So the product of omega. Okay, so Zi hat is for each I it's n numbers. The product is fixed by the gauge coupling constant, but which leaves you with n minus 1 parameters. And so these are dynamical parameters. So that way you have n minus 1 dynamical parameters times R. And the total dimension of the phase space will be twice that. So because that also includes the integrals of motion. Okay, so now this is Lux operator, and no, A's are just integrals of motion. Yes. Okay, once again, so we have A alpha S. So A alpha S. Right. So these were our parameters. So we don't get more parameters by orbifolding. Right? So how many parameters we have here? So we have n, and we have r plus. Okay. Originally we had r plus 2, but we of these r parameters which are correspond to dynamical gauge group plus 2 which are in masses. Okay. Now out of its n parameters, because of this relation, the centers of masses are sent to masses. So these are dynamical plus 1, which is the external parameter, which is the mass parameter. So you have n minus 1 times r Coulomb moduli. So these are the parameters of your theory. In fact, that should be the genus of the curve. Yes. So they count. So for each of these rank n shifts, the parabolic structure of the shift along the curve requires additional parameters because now the quotients can have non-trivial first-Chern class. So I'm counting all of those, and these are the counting parameters. Right. Okay, so this is called, so this is going to be the Lax operator of Gaudin Garnier system on genus 0 curve with r plus 3 punctures, additional punctures being at 0 and infinity. So in order to make from this Lax operator an honorable Higgs field, we multiply it by dz. And so maybe divide by z also. Multiply by, right, so the Higgs field is dz over z times this Lax operator. And I don't have time to verify that when z goes to 0, when z goes to infinity, this operator approaches the diagonal matrix whose eigenvalues are determined by the masses, by these masses. So these are the eigenvalues. So these eigenvalues of the residue of phi at 0 or infinity. So it's a Hitchin system on kind of meromorphic Hitchin system where the Higgs field has generic eigenvalues over 0 and infinity, but has rank 1 residue over the points z0, zr plus 1. Maybe I overdid it, so maybe. Oh no, it's okay. So we can scale. I mean, with the, so these guys z were defined up to overall scaling. So I can set one of them to be 1, and so then you'll be left with r parameters. Okay. All right. No. The symmetry has been completely. There is no symmetry. No. The symmetry was used in constructing this, but it can totally disappear. The symmetry is who has what? Okay. So since LIs are rank 1, so these are rank 1, so they can be written as products. UI, when U is a vector and V is a covector, there is a symplectic structure. So these are. Okay. Very good question. Very good question. So how come? Where is the Poisson structure? So we need to think about the following: that if we take the expectation value of the surface defect, so this is the expectation. So this is the. Okay, let me just write it. So it's a surface defect expectation value. If I compute its derivative with respect to ZIS, for example. Okay, almost by definition. So first of all, if I compute the derivative with respect to Q S omega, if you normalize it properly, so that will give you the expectation value of the just maybe multiplied by epsilon 1. So this is going to give me something like AS omega plus epsilon 1 S omega. So this is the expectation value of the fractional instanton charge, which you can extract from the expansion of the y observable at infinity. And in the limit, in the classical limit, epsilon 1, epsilon 2 to 0, so this psi will behave in a quasi-classical way when S depends on whatever parameters we had. So Zi, Zs omega, A, S omega, and so on. And so this relation will become the relation that the derivative of S with respect to Z will give you the actually entries of u and v vectors. Now, the way to understand this relation is that this is the Hamilton-Jacobi potential, which expresses the momenta through coordinates. And so this is where you can derive the symplectic structure on the residues of this Lux operator. So this enumerative geometry produces for you kind of a Lagrangian subvariety in the phase space of this integrable system, which is generic. So we describe this phase space not point by point, but Lagrangian subvariety by Lagrangian subvariety. So Z modulo the relation, which is the product is equal to the positions of these points, are the dynamical variables. So they're the coordinates on the phase space, and momenta are derived from this Lagrangian subvariety. Okay, so after we've grown the muscle with the finite A-type theory, there is a similar but slightly more complicated formula for the original A0 hat theory, which involves the infinite product in both directions, which is the kind of the matrix version of the product formula for the Jacobi theta function. And the formula for Jacobi theta function has a left-hand side and the right-hand side, and so the left-hand side will have the product of these guys, where the role of yi will be played by y hat without I, because there is only one gate group, but it's shifted by epsilon 3, and so I now becomes an integer valued. And the right-hand side will have the QQ characters, which again are shifted. So and these interesting products will contain, so they will become like q to the quadratic function, and so this is the right-hand side of Jacobi identity, except that it's now dressed with QQ characters and matrices. Infinite product, infinite. Here it's finite because it's a finite Dynkin diagram, and for the affine case, the product will be infinite, as in Jacobi triple identity, which. Okay, we should, so we now call it like it's a boson fermion correspondence, right? So it's a correspondence between Fock space built on fermions and Fock space built on bosons. That's the way we prove it. Right, and you can, so there are different, so in this approach, Jacobi is actually A0 hat. It's not SO2. And then out of that, by, again, with song and dance with projections, you can get any Lie algebra. And so the analog of this D hat will be the yet another representation of the Lux operator of elliptic Calogero-Moser system found by Krichever, but which keeps showing up new faces. And so as this problem, Igor's legacy is keeps going on. So I apologize for going over time.
Let's thank Nikita for wonderful.